Hi, it's time for another math easy solution. Time to discuss further into the hashtag Tengri137, the online cryptic series of alien math puzzles. And now look at part 8, and this is some controversy. This is MES cheating, that's me, and now I'll also look at calculations by hand, because you'll see it in a bit. So anyways, recap my last video in part 7. I went over calculation of Tengri's mathematical name, and yeah, so this all stems from that calculation. So now let's just jump right in. So part 8, MES cheating on the alien math exam, question mark, hashtag for some context. So recall from my last video that I showed how hashtag Tengri137's name, or their number name, based on a calculation was made. So I showed how it was made and showed how you can make your very own name. Here is the quote name and the resulting calculation. So this is from Tengri137. Plug into a calculator, you get a giant number like this. And in fact, all of these are prime numbers, and this is a repeating pattern of 46 digits that can go from zeros all the way to the 8. Or from this way, you could consider the repeating differently, but basically there's 46 digits, and all these are supposedly special physical constants in there, and then I showed how to do that. But for some very strange reason, Defango, the popular YouTuber going through all these puzzles, he did a hit piece on me. Hashtag what the F. So here's a link to his YouTube video. You could check it out. And basically in it he goes over my last video where I used Wolfram Alpha. I didn't know you're not allowed to use a calculator. And I showed how it's pretty amazing. You can plug this in and then do a bunch of stuff on it. So then his title of the video was Easy Math Solutions Cheated on the Alien Math Test. Wolfram Alpha Makes Math Easy. Tengri137. So then he states, I'm kind of at a loss. I can't believe Math Easy Solutions would cheat like that on the tests. Good thing Tengri137 is here to help us. We could have ended up like in Pixels and Cheaters. I don't know the reference. So basically in that video, Defango claimed that I, quote, cheated by using Wolfram Alpha calculator to solve the whole puzzle, which anyone, quote, anyone could have done if they had a calculator. That's what he's basically stating. And that hashtag Tengri137 said you can't use tools. Whoops. So you can't use tools. So why was I not told about this until part 7? Because remember, I've done already part 1 to 6. Nothing happened. No one complained. And in fact, Tengri gave me a thank you message. So why did Tengri give me a thank you message knowing that I had used Spreadsheet, quote, tools in my earlier videos? Hashtag questions. So regardless of those questions, I will show that it is impossible, or pretty much near impossible, I don't know how, any other way of putting it, just to be 100% clear, it's near impossible, pretty much impossible, to solve this Tengri name calculation by hand because of the large prime factorization required in the calculation. So first off, in the calculation that Defango showed in this video, he is wrong in that I used Wolfram Alpha to solve the puzzle, but rather I was showing that the 9s pattern works by using Wolfram Alpha. The only time I used Wolfram Alpha that I actually needed it was this prime factorization, which I'll get to. So let's try solving the Tengri calculation name, quote, by hand. Let's first establish the following pattern. So let's look at the division 1 divided by 9. Now if we want to use long division, and basically you could do this long division. This is the same thing as writing 1 over, 9 like this, and then you put a 1, so that we're doing long division. And if you want to learn how to do long division by hand, I'll put a link to the video in the description below, so check it out. But basically to do long division, so we would do like this. We put the numerator here, the denominator on the left side. Now 9 goes into 1 0 times, so we put a decimal place on this, and then we add a 0. So now we look at it as if it was 10, or another way you could just put the 0 here. So 0 times 9 is, well, 0, subtract this 1, bring this 0 down, so now we have a 10. 9 goes into 10 once, and 1 times 9 is 9. Subtract this, we get a 1, add another 0, carry the 0, we get a 0. 9 goes into 10 1. And then basically do the same thing. 1 times 9 is 9. Subtract, we get a 1. We put this down here, we get another 0, etc. etc. So this all becomes 0 zeros, and then 9 goes into 10 once, and etc. You just get 1 1 1 1, and it just repeats on and on forever. So we put the arrow on top like that, a line indicating that it's repeating. So now let's look at 1 divided by 2 nines. So if we have 1 like this divided by 2 nines, same thing, we do this now using long division, do it like that. So we have 1 and then 99. 99 goes into 1 0 times, put a decimal. 0 goes in here, so do this, 0 times 99 is 0, subtract this. Well, what we get is 1 minus 0 is still 1, carry the 0. 10. 99 goes into 10 0 times. So again, 0 times 10 minus 0 is just 10. Now we carry another one here. We have a 0. Now 99 goes into 100 once. And then same idea. So this goes 99. And then this is going to be subtract this, that's a 1. And again, when you put the 0 in, we get still 0. So put another 0. And then when you put another 0 in here, and this is just skipping those steps. So now we have 99 goes into here once. That's all I got, 99. Subtract this, and we get a 1. Same idea. You bring this down, put a 0, put a 1, etc. And this goes 0, 1, it keeps going on and on. And now the repeating pattern is 2. Now we have 0, 1. So 2 digits are repeating. So that's 2, as opposed to here is just 1. And now one more to show you the pattern, to illustrate this even more, is when we look at 3 nines. So 1 divided by 99, 9, like that. So 999. This same thing is writing it like this, 999 over 1. So 999 goes into 1 0 times, put a 0, and then basically I'll just do this again. Yeah, I'll just save time by putting another 0 in here. Or I'll just put that down right here. So 1 minus 0 is 1, carry the 0, 10, still nothing goes in there, put another 0, now we have 999 in 100, it's still that's 0, it doesn't go into it, and then we put another 0 down, now we have 1,000. 999 goes into 1,000 once. And then 999 multiplied by 1, we get 999. So yeah, when you put this inside, subtract, we get, well, 1. 1,000 minus 999, that's just 1. And then the same pattern occurs. Put a 0, 0 goes, 999 goes into it 0 times. Put another 0, that's 100. This goes into it 0 times. And then you put another 0, and there's 1,000. 999 goes into it once. Then this becomes 9, 9, 9, subtract, this becomes 1. And then same thing, we keep going on, 0, 0, 0, keeps going on, then we get 0, 0, 1, 0, 0, 1, and now we have a repeating pattern of 3 digits. It goes 0, 0, 1, etc. So this is 3 now. So notice the pattern. Yeah, so thus what we have is, we have 1 over, for example, 1 over 9, this equals 2.1111, then the 1's repeating, keeps going on, and then 1 over 99 equals 2.010101, etc. keeps going on, and then we have a repeating 2 decimals. And now for the third one, let's go 3 nines, same thing, but now there's 3. 0, 0, 1, 0, 0, 1, 0, 0, 1, etc. keeps going on, and notice the pattern. Now there's 3. Now if we were to go, let's say, a lot of 9s, and then you understand the pattern. So we have 9, 9, 9, etc., 9, 9, 9. This just equals 2. So this is going to equal to 0.0000, etc. keeps going on, 0, 0, 1, where this is the repeating pattern, dot, 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 and it just repeats. So this goes on, and this is the same as the number, number of, quote, nines. So basically the number of 9s in that. And there is our pattern. And now note that this works for any numerator, which is the number on top, assuming it's less than the denominator, not just the number 1. The denominator is the bottom. And this is because each number can be broken up into a sum of fractions. For example, instead of 1, we had, let's say, number n. So n could be anything as long as it's less than the denominator. So n divided by 9, this equals to, this is the same thing as writing n times 1 over 9. So just remove that out. This equals to n times, and we already know what 1 over 9 is, 0.11111, etc. So this equals to 0.11111, dot, dot, dot. And now we could break up this whole thing into fractions. This is the same thing as writing, n times, now we're going to split this up into, well, this 0.1, that's the same thing as writing 1 over 10. So then that's the same thing as adding 1 over 10 to, now this one's going to be 2 zeros, 1 over 100. And now the third one, this is the same thing as 3 zeros, 1 over 1,000. And as you can see, so this one goes there, this one goes here, this goes here, then this is plus 1 over, actually this one is over this one. And this one across here is 4 zeros, like that. And then as you can see, it just keeps going on and on forever, and all we do is add another 0. That's pretty much what this decimal places mean. So now that we have that, we can multiply this n inside. So when we multiply, we get n over 10 plus n over 100 plus n over 1,000 plus n over 10,000, etc. plus, and all this means is, all this means in decimal notation or decimal form, this goes point n, that's this n over 10. Now this n over 100 is over there, this one goes here, and this one goes here, etc. And then we end up getting n, etc. So that is our pattern. So now this means, well, that we can write any number in a variety of repeating ways, even the exact calculation that hashtag Tengri137 used. So what they had was this giant, this prime number multiplication on the top and bottom, and then the final answer was this part where this is repeating. Notice that this has a period of 46. So first of all, to make it easier, I will call Tengri's repeating non-zero numbers the pattern as t. So I'll look at this from 7 all the way to 8, and I'll just call this t, number t, just because it's easier to deal with instead of just writing this giant number. And again, to show you that it could be anything. It doesn't matter what it is. We could still make it repeat exactly like this. And then the only difference is, well, since it has a period of 46, notice it's 46 period from here to here, or you could look at from the zeros all the way to the 8, still 46, and that just means that the t has 40, I'll just put the over here, so 44 digits. So it's 44 digits, but there's 46 nines, that's what we have, because it's a period of 46. So because it's a period of 46, as we showed above, this is the same number, so the period represents the same number of nines. 3, there's a 3. 2, there's a 2. 1, there's a 1, etc. So now you see the pattern. And now since it's a period of 46, basically there's 46 numbers, including the 0 zeros. Excluding it, the t is just 44 digits. So that is all. And thus what we have now is we have t over 999, etc. Keeps going on and on, 999, and where this whole stretch of numbers is like that. This is 46 quote nines, like that. So that's 46 nines, and because the t has 44 digits, this is going to be 0.00 and then t, 00 t, 00 t, 00 t, etc., etc. There is our repeating pattern, and this is pretty much our answer outside of the prime factorization. And I will box this in. So there is our proof that that's the repeating pattern. We don't need to do pages of calculations to get, I don't know, whatever number of decimal places. We've already proved for infinite number of decimal places, as opposed to Defango was talking about, where he's talking about you have to prove doing a bunch of calculations on paper. I don't know what that means. I just proved that it's infinite. So infinite more than how many pages you're going to do. So so now that we've set that up, and now we need to perform the prime number calculation. So to obtain the prime number calculation, we need to perform prime number of factorization. And basically what we need to do is show that this whole number I'll cross on the left, so t over 999, etc., 99 equals to, well, this Tengri calculation. That's what we need to show. And again, that is 46 nines. So again, it's just hard to write, but you get the idea. And again, remember prime number factorization. For example, 30 becomes, well, this is 15, this is 2, so 15 times 2 is 30. And then you can split up the 15 into 5 and 3. So then basically this means that 30 equals 2, 15 times 5 times 3 times 2, and these are all prime numbers. That's prime number factorization, just for a simple case like that. But what we want to do is show that t is equal to all the way across here. The 999 gets to something like that, which is just very large numbers on prime number factorization. So now let's read up on prime number factorization first. So yeah, just to get you a quick overview of prime number factorization, if you go to the integer factorization page on Wikipedia, so let's just read up a bit. So in number theory, integer factorization is the decomposition of a composite number into a product of smaller integers, exactly what it did here. So 30 composite number into a bunch of prime numbers. Well, that's when you're looking at prime numbers. If these integers are further restricted to prime numbers, the process is called prime factorization. So I've reduced this the most. Just basic integer factorization is from 30 to go into 15 times 2, but then we can go further all the way to the most unique version of it. When the numbers are very large, though, no efficient non-quantum integer factorization algorithm is known. An effort by several researchers concluded in 2009 to factor a 232-digit number, so much larger than the 46, but nonetheless, 46 is very, very large. So this number, utilizing hundreds of machines, took 2 years. So 2 years to factorize to prime number factorization of a 232-digit number with hundreds of machines. But then when you're just using a calculator online for 46, even that's still quite impressive actually, 46, but nonetheless super hard. So the researchers estimated that a 1024-bit RSA model would take about 1,000 times as long. So yeah, there's a lot of computing power in it. However, it has not been proven that no efficient algorithm exists. The presumed difficulty of this problem is at the heart of widely used algorithms in cryptography such as RSA. Many areas of mathematics and computer science have been brought to bear on the problem, including elliptic curves, algebraic number theory, and quantum computing. Thus, it is basically near impossible. Well, I'm just going to state impossible, bracket near, because I don't know any other way. If you do know, let me know, or if the numbers that Tengri used were just somewhat easier to factorize. But basically, thus it is near impossible to perform prime factorization of very large numbers by hand, especially 46 digits numbers. In fact, most online calculators can't even perform such calculations. So even if you use a calculator, you're not always going to be able to do it. For example, if you go to this emathhelp.net, they say numbers should be an integer greater than 1, but less than 1,000. So I tried using it. You couldn't put 46 in there. This is 10,000, less than 10,000. So you can't factorize that. I tried putting 999 inside that maths is fun, which I referenced in my last video, and they say that please enter a number between 2 and 9 something, but this is much less than 46. So this is 1, 2, 3. This is 6, 9, 12, and then this is 15 digits. So 15 digits, and then Tengri's is it's pretty much triple that. So 3 times this. So these guys can't even do it. So luckily for us, the amazing Wolfram Alpha calculator can do so. Hashtag amazing. So yeah, there's many ones you can't even do it with a calculator. Luckily, Wolfram's got a pretty sweet one. So if you plug in the 999, this is 46 digits. What we end up getting is this prime number factorization, 3 squared times 11, etc., all the way here. And then when you plug in the t number, this is our t on the URL. So this equals to t, that Tengri number. And then we get this to 2 times 3, etc., all the way across. So thus what we end up having is, this. Well, this number here, or this t, this t divided by this number across. That's the denominator. Should have had it other way around. So anyways, when you put that around, we get this division. So this across. But notice what we could do. We could simplify by canceling the like primes. So 3 cancels with this 3 squared. So then all we're left was with a 3. So basically now what we finally get is this is the Tengri 137 name. So this simplifies to it when you cancel this 3. So now we have 2, the 3 is gone, 2, 23, 49, etc. And this is 515, this is exactly 06, etc. And then the bottom, the 3 squared cancels, we're just left with 3, 11, 47, 139. This is 111s. You could double check, count it up. It's the exact same. So what this means is our pattern gets the exact Tengri number by using the prime factorization with Wolfram Alpha. This is the 999, etc. pattern, which I just discovered. Well, I just did it by hand. So now I would double check my work using Wolfram Alpha, but I am worried. I'm worried Defango might take it out of context and say that someone as a type of basically take it out of context and say that I'm using too advanced AI. I don't know, a hashtag LOL. And also as Higher Minds guy on Twitter, he tweeted, deserves a poll, who would win a math battle, Wolfram Alpha, some weird app using Apple Siri, Assistant and PG-13 on Play Store, or an advanced alien race that communicates with complicated puzzles, giant brain, there's Tengri, and then obviously I retweet, great idea, new poll, and I made a new poll, what is more powerful, advanced alien tech, super duper Wolfram Alpha, or, thought I said no polls, but the winner so far, 4 votes, don't stop polling us. And now my challenge to, or counter challenge to Tengri 137. How is it possible to perform prime factorization of a 44 or 46 digit number by hand? Can you please provide us a way? Because Defango said we can't use tools. If we can't use tools, so how are we going to do this by hand? That's pretty much impossible. So if you can, if you can find a way, then you just might be able to break the internet, because many security systems rely on the difficulty for computers to perform prime factorizations of large numbers, albeit larger than Tengri numbers, but same idea. If you could do this by hand, then basically what it means is if you had a calculator doing this by hand, doing the calculation or the method that you did by hand, you can break the internet. Break and shatter the internet and then hack into CIA, etc. So I also may look further into the hashtag Tengri 137 puzzles, because I find them very cool. So stay tuned for more of what I discover. Hopefully I don't get another hit piece on me. But anyways, thanks for watching. And again, if you know a way to do this prime factorization of these 44 or 46 digit number by hand, please let me know. Even if you know how to do it without by hand in a faster way than, well, these calculators can't even do them, which is quite amazing. Just let me know. Anyways, that's all for now. If you learned how to do this by hand, learned a bit about the calculations and divisions, again, if you want to learn more about division by hand, check out my earlier video. I even do an extensive video on why division by hand works the way it does. Anyways, thanks for watching. Like always, you download these exact notes in the link below, and yeah, stay tuned for another math easy solution.